to this video as we are going to explore graphs of what we call power functions, okay, which basically means that it is y equals to a number, a positive number, a real number, x, which is a variable, can be any numbers to represent x, and n, which is a rational number. And more specifically for this particular video, we are going to explore the cases where n is equal to -2, -1, 0, 1, 2, and 3. Okay, so the very first thing is that these are what we call a power functions, okay, which is in this form: y equals to a, which is any real number, x to the power of n. So when n is equals to 0, example, where y equals to a to the power of x, x to the power of 0, this is basically represented by y equals to a, because anything to the power of 0 is, let me use a green color instead. Anything to the power of 0 is actually equals to 1. So x to the power of 0 actually becomes 1. A times 1 is a. Yep. So this y equals to a, where it cuts the y-axis at a, there are some observations that we can actually see. Yeah, it is actually a horizontal line, yes? And when I do it for a negative value of a, meaning negative a power times x to the power of 0, this is also again equals to y equals to -a, because by the same understanding, anything to the power of x, 0 is equals to 1. Okay, so -a times 1 is -a. And in this particular case, it is cutting y-axis as -a, and it is again a horizontal line. So there's a special name given to this type of function or graph. It is called a constant function. Okay, and it is a what line? Just now I mentioned before. Horizontal or vertical? Very good. Horizontal line. And it passes through the point 0, a. Okay, which is basically this point here. Let me just use a red color, which is this point here, which is the y-intercept. Okay, so basically this is the y-intercept. Let's move on to the next case. Alright, for case number 2, we are exploring the case where n equals to 1. So the example will include y is equals to ax, because x to the power, the n is 1, right? 1. And this basically means that it is actually y equals to ax. Okay, and when I plot this graph, you do see that it is actually a straight line. Gradient actually is represented by a. As we explored previously, y equals to mx plus c, the number in front of x, the coefficient of x is the gradient. Yeah. So this a actually from here we go actually gather that the a is representing this gradient of this straight line. So this is a linear function, okay, a straight line graph. So if it is a y equals to negative ax still to the power of 1, then it is simply y equals to negative ax. Again, it is a straight line, but because now the gradient is negative, it is sloping downwards. Yep. So this function is a straight line graph. It is a straight line. With gradient represented by a. And it passes through, for this particular example, it passes through what we call the origin, which is this point here, the point at the center of the axis. Let's move on to the next case where n equals to 2. Hello everyone, welcome to this part of the video where we are going to explore the case where n equals to 2. So given the equation, x to the power of n, now the n is 2. Alright? And if a is negative, then y will be equals to negative a to x to the power of 2 as well. And we do have seen such questions before. And the shape is what we have seen before as well. It is either a U shape or an inverted U shape. And very importantly now, we also know that there are lines of symmetry. So in this case here, the lines of symmetry is actually the y-axis for both cases, and this happens where y-axis, the equation of the y-axis is x equals to 0. Previously, we also known that this type of equation where the power of the variable x is 2 are known as the quadratic equation of functions. And if it is a U shape, then it is opening upwards. And if it is a negative, a is negative, inverted U shape, so this is opening upwards, then this one will be downwards at the other direction, as seen from the graph on the right side of this video. Last but not least, another observation is this particular point here, where we actually turn. This is where we call the turning point. And the turning point is at the origin. With that, we have come to the end of this part of this case where n equals to 2. Let's continue to explore the other cases. Hello everyone, welcome to this particular part of the video where we are going to explore the case where n is equals to 3. So example then would include like y equals to a when a is positive, x power 3, and here will be a equals to negative a x power 3. Negative when a is negative. Do take note at this point that this is the shape of this particular graph. Okay, and At this point, I do want to label the quadrant. This is how we label the quadrants. First, second, third, fourth quadrant. Same goes for the other side of this particular graph where A is negative. There's a special name given to this type of graph where the highest power for the variable x is 3. We call them the cubic function, and it has to pass through. For this case, another observation that they actually is that it passes through the origin. And for the part for this graph, do take note, it lies on the first and third quadrant when A is positive, and when A is negative, it lies on the second and the fourth quadrant. The last observation that we can see is actually that the graphs for positive and negative, actually it has a rotational symmetry of order 2 about the origin. Okay, again, yes, something. This origin came out again. It passes through the origin, and the graph actually, if we were to rotate it for the case where A is positive, if you were to rotate it, it will actually be able to rotate to the graph when A is negative. So there is a rotational symmetry of order 2. Alright? And we have come to the end of this part of the case. Let's continue to explore other cases. Hello everyone, welcome to this part of the video where we are going to explore the case where n equals to -1. So this means that we are going to see y as equals to ax power -1. And there's another way of writing this though. Okay, the other way to write this will actually be that the a, but the x, because the power is -1, I could actually write it as a denominator such that when I do that, the power become a positive index. Okay, this is what we learned in the law of indices. So same goes for the case where it is a negative. A times x to the power of -1, we can also rewrite it as -a over x. X power 1 and x actually are the same thing. Okay, so if I rewrite it from numerator to a denominator, the power changes. Alright, so now this is the graph of y equals to ax -1, which can be expressed as y equals to a over x. Notice for both cases, either where a is positive or a is negative, it actually has two curves. 1, 2. Same goes for the case where it has, where the a is negative. Two curves. And also notice, it does not intersect the two axes, meaning it does not touch the axis. And so, let's move closely to the first part, okay? Where we shall look at the case where a is positive. It actually lie on the first, this is first, second, third and fourth. It actually lies on the first and the third quadrant. Then when A is negative, again, if I were to write first, second quadrant, third quadrant, and fourth quadrant, when A is negative, it lies on this second and fourth quadrant. And the next two lines, when X approaches 0, let's see what happens, okay? When X approaches 0, that means we are actually looking at along the y-axis, along here, where X either go this way or go this way. What happened to the graph? Do you realize that it either get very, 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 very large, as seen here in the first quadrant, or it will get very, 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 very small for the y value in the third quadrant. So it can get either very large or very small for the y value when X go towards 0. For both graph. Same goes for this also, you see. This is the y-axis, right? Then when X is going to be towards 0, meaning here and here, you do see that it either go very, very large here in the second quadrant for the case where A is negative, or here the value of y becomes very, 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 very small. But here's the catch. It never touches the y-axis. Then, when X becomes bigger and bigger, or smaller and smaller, what do you see? What happens to the value of y? The value of y actually becomes smaller and smaller until it's trying to reach 0, but it doesn't reach 0. Okay? It never touches the x-axis. Alright, so these are some of the observations. And lastly, same as the cubic function, this graph actually has an order, rotational symmetrical order of 2 about the origin. Alright. And with that, we have come to the end of this video for this part of the case when n equals to -1. Let's continue to explore another case, shall we? Hello everyone. For this part of the video, we are going to explore where n equals to -2. So this is the example. Well, same as the case where x equals to -1, we can rewrite this equation as y equals to a over x power 2, positive. Okay, we can do that by using the law of indices. So this is same goes for the -a. So -a over x power 2. Same thing. If I write the variable x as a denominator from a numerator, then the power changes from positive to negative or negative to positive. And so this graph is of this family y equals to a x -2, which can also be written as a over x squared. Again, you should see there are two curves, one here and one here, broken up, one here and one here. It does not intersect the two axes, and for the case where it is bigger than 0, do take note again, this is first, second, third and fourth quadrant. It lies on the first and second quadrant when it is positive. And what happens to the value of x? Interestingly, as the value of x goes towards 0, which is here, Do you realize that the y keep on increasing until it becomes very, very, very large, but it does not touch the y-axis? Okay, so this is for the case where a equals to bigger than 0. As for the case where a is less than 0, which is the right side graph, do notice that again this is first, second quadrant, third and fourth quadrant, that the graph lie on the third and fourth quadrant. And again, the value of x, as it approaches 0, which is around here, what happened to the value of the y? Yes, it becomes very, 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 very small. The y keep on decreasing. Okay? And the next line that we are going to explore now is that as the value of x become very, very large or very, very small, what happens to the value of y? Yes, it approaches 0, but it does not touch x-axis. So it will not be equals to 0, but it can get really close to 0. Alright? For the last part, there's one more thing to talk about this particular graph. Do you realize that there's a line of symmetry here? Yep. Yes. So it is symmetrical about the y-axis, where the equation of the line is x equals to 0. With that, we have come to the end of this video. So if you like this video, do give it a thumbs up. Thank you for watching and have a nice day. Hello everyone. For this question, we are supposed to match these 6 equations to these 6 graphs. So we do need to know the shape. So let's see. For this 4 over x squared graph, if you refer to your notes page 3 over x squared, you do see this is the shape. This is for positive and this is for negative. Negative 1 over x squared. So I go back to the graph again. I see negative. Alright. 4 over x squared. So I go back here again. Negative x squared. 1 over x squared. So I now know the shape. So I go back to this particular 6 graph to see which one has the shape. Yep, you guys have seen it as well. So this is for graph number I1. Graph number 2. Again, I look up for this. Is it positive or negative? And what is the power? So in this case, this is over x power 1. So I go back to the notes, page 3 again, and I saw it. 1 over x. This way. Negative 1 over x. This way. So I go back to the question. Negative 2 over x power 1. 2 over x. Do take note the number on top. Only tell us how high the shape, the graph is, but the shape is the same. Negative, negative, over x, over x. So now I know the shape is this. So I go back to here, and I saw it. Negative. So this one will be my graph number 2. Okay? Part 3. Y equals to negative 4x squared negative 4x power 2. This is relate back to chapter 8. So an x square graph. If you notice on page 2 of the notes, x square graph, positive x square, a U shape, negative x square, negative x square, an N-shaped graph. So once I know the shape, I go back here again. Negative, negative, x square, x square. So I know it's this shape. I go back here. Anyone with this shape? Yes, yes, I saw it. So this is graph number 3. Graph number 4. Y equals to negative x power 3. Negative x power 3. So again, I go back to my notes. X power 3 graph this way. Negative x power 3 this way. So I go back here. Is there any shape that looks like this? Yeah. This is the one. Y equals to 4 over x. Again, 4 over x, positive, positive over x, so it's this shape. So this one will be my graph number 5, and of course the last one, just to make sure that you guys are able to spot it, it is a positive x square graph, positive x square graph, U shape, and it is indeed U shape. This concludes this example. For this question, we would have to sketch this graph. Step 1, I need to know the shape. Over x square graph, I get back to my notes, page 3 of my notes. Over x square graph, the shape looks like this. So now I know the shape is like that. Step 2, I need to know whether y equals to 3 over x square passes through 1, 3. So how do I know it? I substitute x equals to 1. If this graph passes through this point, the y has to be 3. So let's see. Y equals to 3 over 1 square, 3 divided by 1. Yes, 1 and 3. So this is indeed passes through this point. So I now know the shape. So my pencil, the shape looks like this. Symmetrical. That means to make it really neat, it's about 0.9. So 0.9. Make it symmetrical, and also, of course, it will be good for you guys to plot this point as well. And that, last but not least, yes, please write this down as well, the name of the graph. Next part, K. 27 is a point on this graph. Find the possible values of K. So in this case, I'm going to substitute K27 into y equals to 3 over x squared. So x will be K, this is x, this is y. So 27 equals to 3 over K squared.
times k on both sides. Divide by 27 on both sides. So 3 over 27, if you guys realize, is 1 over 9. So square root 1 over 9, 1/3. But every time you square root, take note, every time you square root, you will either have a positive or a negative answer. That's why possible values of k. So it's either 1/3 or negative 1/3.